For section 1.3, we're going to start with just a lot of vocabulary. So I'm going to go through this kind of at my pace, but keep in mind that you can feel free to pause this, copy this down as you need to, and also keep in mind that I will be checking notes, so this is not something that's optional. But let's go ahead and start with the number line. So when I'm dealing with the number line, we know that if I look right in the middle of the number line, kind of the center of that would be 0. Everything to the right of 0 we represent as a positive number, so those would be all our positives, 1, 2, 3, 4, 5, 6, so on and so forth. Everything to the left of 0 we classify as a negative, so that would be our negative 1, 2, 3, 4, 5, 6. The further we go to the right, the higher the positive. The further we go to the left, the lower the negative. We also classify these in different categories. So, for instance, and this is stuff you we'll need to know for the test, so I would encourage you to write these definitions down, and as you go through the homework, if there's any that you're not certain about, put them on a note card and have those ready. But our first type here is going to be counting numbers. And kind of my history for this is this is all of our positive numbers, all our positive whole numbers except for 0. And the main reason we do that is that 0 is actually a pretty complicated idea. There is no 0 in Roman numerals, for instance. In fact, the first culture to come up with the idea of a 0 that we have historically was in the Americas. We had, I believe, the Aztecs had a representation for nothing. So if I'm counting something, you're like, well, why do I start at nothing? And in mathematics, we have a lot of reasons to have a 0, but that was not intuitive. So when we do our counting numbers, that's just like, well, you don't start counting at 0. You start counting at 1, 2, 3, 4, 5, and this represents the set of all numbers, all whole numbers starting at 1. When I say the term whole numbers, though, that whole numbers includes a 0. So that's the only difference. As we're going down, we're basically adding things. So, for instance, everything that is a whole number is also a counting number. The 1, 2, 3, 4 is up here as well. 1, 2, 3, 4. The only thing we added when we say whole numbers is that 0. When we talk about integers, that takes us past to the other side of 0. So instead of just being 0, 1, 2, 3, 4, 5, we now have negatives on that. So here we had, let's see if I can kind of color code this, all of our counting numbers with these yellow positive whole numbers. Whole numbers included all those as well, but added that 0 from before. That is not the color I wanted, so let me try that again. The 0 there. And then what happens when I do integers? Well, we still get all the positives on the right, but we also now add all the negatives on the left. And so basically everything that is a counting number is still a whole number, is still an integer. 3 is in all 3 categories, but not everything that is an integer necessarily is a counting number. Some integers, like all these yellow ones, are going to be in the top 2 classifications as well. So these are kind of our definitions: counting numbers, whole numbers starting at 1, whole numbers starting at 0, integers, we now add both positive and negative. This is called set notation, the symbol that we're using. It's a little like braces, and then we put all the elements there in the middle. So this is not something I'm necessarily testing you on, but it is something we do a lot more in Math 51, and I wanted to make sure that you had seen that term and know what it means. Another term that they're going to be using, like I said, a lot of definitions, is if I say the opposite. What is the opposite of a number? Well, physically, if I'm talking about the number line, it's on the opposite side of 0. So if I do the opposite of 5, I go up to the number line, I find 5, and if I were to jump all the way to the opposite side of 0, I would get to negative 5. So the opposite of a positive is a negative. What about the opposite of a negative? See, what if I went up here and I started way back here at like negative 16 and I jumped to the other side of 0, right? Where would we end up? Well, if we jumped to the other side of 0, that would no longer be negative. It's the same distance. We jumped equally to the other side, and so it would be positive 16. That would be the opposite. This gives us a good reason for basically thinking about opposite of. If I say opposite of, basically we put a negative in front. So the opposite of negative 16 is negative 16, or just positive 16. That's a little more than you need for this section, but that's going to be something that we're going to be building on in the future, that when I do the opposite of a positive, I always get a negative. If I do the opposite of a negative, I always get a positive. We can do different sets, and they're going to have you doing some of this in the vocabulary. If I said the set of positive even numbers, well, I know I'm dealing with only positives, but evens mean I'd be doing things like 2, 4, 6, 8, and this ... means that those even numbers go on forever. Okay, so hopefully you take a second, write that down. Here's another way of thinking about when we're dealing with integers specifically. If I say the lowest temperature was 190 degrees Fahrenheit below zero, right? That is a situation where we need to have integers. We can't just have positive numbers in real life, because if I have 129 degrees below zero, then that means the temperature was not a whole number, it was an integer at negative 129 degrees. The shore at the Dead Sea is 1,348 feet below sea level. I forgot to put feet in there, but I'll throw it in. Feet below sea level. What does that below sea level do? Well, if I was talking about the elevation, that would mean we would not have a positive elevation, we would have a negative elevation, or negative 1,348 feet. That would be the elevation for the shore at the Dead Sea. So you can have elevations that are above the sea, positive elevation. You can have elevations that are below the sea, negative elevation. Our next type are rational numbers. See, rational numbers are basically any number, x, anything, such that or given that that number can be written as a fraction. Any number that can be written as a fraction is a rational number. That includes all the numbers we have had so far. For instance, 2 is a rational number. You're like, wait a sec. I thought that was a whole number. It is. And it's a counting number. But why is it a rational number? Can 2 be written as a fraction? Yeah. 2 over 1. So basically that means that all of our whole numbers, all of our counting numbers, and all of our integers are all still rational numbers, because all of those can be written as a fraction. Any whole number can be written as a fraction by putting it over 1. So what do rational numbers add? Well, they add fractions. Rational actually has the root word at the beginning, ratio. Ratio means fractions. So anytime I see a fraction, -5, it's not a fraction, but we could make it a fraction. Therefore, it is rational. Something like 2/5, obviously, is a fraction. So that is rational. But we also say, so that's if it can be written as a fraction, any of our whole numbers and any fractions. But we also say, or if it's a terminating or repeating decimal and fraction, okay? So basically any terminating or repeating decimal and a fraction. What do I mean by terminating? Well, I could take 2/5 and I could take that fraction and turn it into a decimal. This we talked about before. This literally means 2 divided by 5. If I put a decimal on a 0, 5 goes into 24 times. So that means if 2/5 is rational, so is 0.4. Why? Because it is a terminating decimal. What does terminate mean? It ends, right? You want to terminate something? It ends. So this is a terminating decimal. Any decimal that ends, that is not non-ending, right? It stops, can be written as a fraction. 1 3/4. Obviously, 1 3/4, we got a fraction, but you're like, yeah, but it's got that 1 there too. Well, a couple ways of doing this. I could turn this into a mixed number by doing the whole multiply and add. I multiply the whole number. I think of fractions as part over whole. This says I have 3 parts, and 4 parts make up a whole. I have a whole of something. I have 1. That is one whole number. If I want to turn that into a fraction, I take that 1 times 4 because I have one whole part. I multiply it by 4 and I turn it into 4 parts. Add the 3 more to it and I get 7 parts where 4 make a whole. This is still a fraction. This is still rational. I could also take that 7 and divide it by 4. Notice what? 4 goes into 7 one whole time. That's that whole number. With a remainder of 3, bring down to 0. 4 into 30 would be 7. Leaves us with 2. Bring down a 0. 4 into 20 would be 5. And this is now terminated. 1 3/4 or 7/4 is the same thing as 1.75. A terminating decimal. That makes it what? That makes it rational. If it can be written as a fraction, it is rational. It can be a ratio. Any decimal that ends, terminates, can be written as a fraction. Any fraction can be turned back into a decimal. That also includes 0. 0, since it was included before, is still rational. How do I know? I could stick it over 1 and it is still 0. I can make it a fraction, 0 over 1, and it's still 0. Therefore, it is rational. What about this 0.3? Well, I already told you 0.3, any repeating decimals, this is going to be rational. You're like, really? But I thought you said ratio means it has to be a fraction. Well, that's what's kind of cool about any repeating decimal can be written as a fraction. This 3, basically, and this is kind of a trick, you take whatever's being repeated, the 3, and you divide it by a 9. 3/9 is the same thing as, divide the top and bottom by 3, 1/3. If I take 1 and I divide it by 3, I get 3 is 9, leaves me with 1. Bring down a 0. 3 makes 9, leaves me with 1. Bring down a 0. The idea is what? As this goes, that 3 is going to keep repeating. Okay? So any repeating decimal can be written technically as a fraction. We could turn that into a fraction. Therefore, it is a ratio or a rational. What about 4.7? That's not a fraction, not a repeating decimal, but you got to remember from before. If it's a decimal that terminates, then it is still rational. Okay? So let's go back up over the definition real quick. Rational, any number that can be written as a fraction. What does that really mean? Any number where the decimal terminates, that was right here, or repeats. And any fractions. So anything that can be written as a fraction, is going to be rational. That's the easy one. But basically what? Any decimal that terminates, or any decimal that repeats. All of those are rational numbers, ratios. Let's take this fraction, right? Where is 4/3? And I love the way this book kind of really goes into some number sense, because my saddest things when I see people take 4/3 and go, I don't know, it's between 3 and 4, right? It's got a 3 and a 4 in the number. Yeah, but no. What does this mean? Remember, we talked about before in the previous section, this says 4 over 3, or 4 divided by 3. So I can take that 4 and divide it by 3. What we divide by goes on the outside. And 3 goes into 4 one time. If I want to continue and kind of see where this continues to go, 3 goes into 10 3 times. 3 times 3 is. Bring down another 0. 3 goes into 10. Oops, sorry, let me fix that. Got all excited there. 3 times. 9 leaves us with a 1. What's going to happen as we keep going? This 3 is going to be repeating. So what would our answer be? 1.3 with a line over it. If we rounded it, then we would stop it at 1.3 or however far they wanted us to. but this is how I would show that that is a non-ending, non-terminating decimal. Okay, so you need to know how to turn those fractions into decimals. Notice 4/3 is not between 3 and 4. What is it in between, really? Well, 1.3 is between 1 and 2. It is larger than 1, but it is less than 2. What about 23/8? I don't know. Take 23 divided by 8. How many times does 8 go into 23? 8, 16, 24 would be too big. So 8 times 2, take it away, leaves us with 7. I could keep going. 8 into 7. I feel like I need more space here. How about 8 into 70? 8 times 9 is 72. That's too big. 8 times 8 would be 64. Leaves us with 6. Another 0. 8 into 60. 8 doesn't go into 60 evenly, but I think 8 times 5 is 40. 8 times 6, 8 times 7 would be 56. Can I stop yet? Has this number terminated or repeated? Then I need to keep going. Okay? I am going to make some extra space here. Sorry, I know this is kind of messy. So I'll just shrink that. I'm sure you can all do that as well. And I'll move this. Alright, we're almost done. 60 minus 56 is 4. Put another 0. 8 goes into 40, finally evenly. 5 times 8 is 40. So notice 23/8 is not between 8 and 23. 8 goes into 23 2 times with some mess. We finally had nothing left, so it is 2.875. You need to know how to turn fractions into decimals. All of those are our rational numbers. Any decimals that terminate, any fractions, any decimals that repeat. Our next category is called radicals. So we were on, let me make sure we're clear, that was on 4. So we are on 5. Radicals are irrational numbers. What is the square root of 8? Like, I don't know. Remember, square root means what number times itself makes 8. And here's where I have some people go, well, that's not, there's no number that does that. And technically, that's not true. You're not completely off the deep end, because for a long time, mathematicians didn't think there was a real number. But we will prove in more advanced mathematics that there are real numbers that times themselves make 8. But what I do is I go, well, I know it's between two numbers. How do I know? Well, I know the square root of 4. What number times itself makes 4 is 2. And I know that the square root of 9 is 3. So doesn't it make sense that the square root of 8 would be between the square root of 4 and square root of 9? Isn't 8 between 4 and 9? Then that means that our answer must be between 2 and 3. Between 2 and 3. What was the other example that we got for radicals? Was we had something like the square root of, I think it was 76. Well, what is that between? Well, we're already at the square root of 9, right? That's not high enough. What's the next number that we get? What is 4 the square root of, right? The square root of, still not high enough. But 5 is the square root of. 6 is the square root of. Still not quite to the square root of 76, right? 7 is the square root of. 8 is the square root of. We're getting pretty close, right? 64 is pretty close to 76. And 9 is the square root of. I know that 76 falls between these two numbers, which means that the square root of 76 must be between 8 and 9. These are called irrational numbers. In fact, if we think about what irrational is, irrational literally means numbers that don't make sense. It doesn't mean they're not real. Just because something doesn't make sense doesn't mean it's fake. But numbers that don't make sense are irrational. The square root of 8 is irrational. It doesn't make sense that there's some number times itself that makes 8. But it is real, and we'll prove that. Okay? But things like the square root of 2, that is a non-repeating decimal. There is an answer to that, but that is a number that goes on and on and on forever. Pi is irrational. If you take any circle, if you take the circumference and divide it by the diameter, you always get pi. Does that mean you always get exactly 3.14? No. It is a number that keeps going on forever. It is a non-repeating decimal. E is another number we see. When we do more in the sciences, you'll see that a lot in Math 51. It's 2.71. Not exactly. In fact, I think it's like 2.715. It keeps going on. It's like pi. It goes on forever. It has to do with science. It has to do with growth. It has to do with things that we see in nature. It is a real number that doesn't make sense. And so when we discover those, we called them irrational. They are still decimals, but they are non-repeating decimals. The square root of 2, if I were to write that out, there is a decimal, but it is a non-repeating decimal. Last couple things. So that was kind of the hefty part, a lot of definitions. This, I actually like this. You need to be able to plot numbers on the number line. Some of them are easy, and we're going to do like an approximation. But like -3, right? -3, I know that it's negative, so we are on the left side. And I know that we're going 3 to the left, so that one's actually easy. We just plot it. There's our -3, right? Done. Where's 17/8? I'll give you a hint. Don't put it between 8 and 17. What do you need to be able to do? Well, take 17/8 and divide it. This basically says 17 divided by 8. I don't need the exact decimal. I just need to know how many times does 8 go into 17? Well, 2. I could do a decimal and a 0. 8 into 10, 1. I could keep going on. I think I'm going to get like another 2 and a 5. But what did I get? I got 2 point something, 2 point mess. What does that mean? Well, 8 goes into 17 2 times. We had something left over, so this number is between 2 and 3. That would be our 17/8. Between 2 and 3, closer to the 2. Where's -2.75? Well, there it's almost easier when they're decimals, right? That means -2.75 is between -2 and -3. 75 means it's closer to the 3, so we put that dot. Where's 1 1/2? Well, I know this is 1. If I go 1/2 more, that's 1 1/2. If you're not sure, you could turn that, and I wouldn't do this, but you could turn this into a mixed number, an improper fraction, and make that 3/2, and do 3 divided by 2, which would give us 1.5. But there's some options there, so that's 1 1/2. -3/4. Do not put that between -3 and -4. Like, yeah, put it between 3 and 4. No. What is 3 divided by 4? What's interesting this time is the 4 doesn't go into the 3. Not even once. And it doesn't go into any whole times, right? 4 goes into 37 times, but that doesn't make that 7. That makes it 0.7 when I bring that decimal up. Leaving us with a 2, bring down the 0. 4 into 20, 5. 5 times 4. So what are we looking at here? Well, don't put it at positive 0.75, because don't forget it was negative, but basically this is the same thing as negative 0.75, or -3/4, right? Where does that really go? Between 0 and -1. That would be our -3/4. And last but not least, where the heck does the square root of 6 go? What number times itself makes 6? I don't know, but I know what it's between. I know that the square root of 6, I can't do the square root of 5, but I can do the square root of 4. The square root of 4 is 2. I don't know the square root of 6. I go up now. I don't know the square root of 7. I don't know the square root of 8, but I do know the square root of 9 is 3. So doesn't it make sense that if the square root of 6 is between 4 and 9, right? that our answer must be somewhere between 2 and 3. Somewhere between 2 and 3, we're going to put that square root of 6. So you will need to be able to do that. There are going to be some questions to give you lists of numbers, but they're going to give you pictures. So if you can do this on the paper and kind of match it on the picture, something you can expect to be able to do on the test. Let's keep going. It says true or false. Is negative 2 less than 4? What does less than mean? Well, we know it means below then, right? But what does it mean on the number line? Well, it means a number that is further to the left. Any numbers to the left are less than. Any numbers to the right are greater than. Is negative 2 less than 4? That is true. How do you know? Here's 0. To the left is negative 2. To the right is positive 4. So since negative 2 is further to the left, that makes it less than 4. Is 6 greater than negative 3? If less than means further to the left, greater than means further to the right. So here's my number line again. 6 is over here to the right. Negative 3 is over here to the left. Is 6 greater than, further to the right, than negative 3? That is true. Is negative 9 less than negative 12? Here's where I start catching people. People look at this and go, yeah, absolutely, this is true. Is negative 9 further to the left of negative 12? Well, if I had my number line, and I went back 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 12 would be further to the left. Is negative 9 below negative 12? Is negative 9 to the left of negative 12? That would be false. You're like, that makes no sense. 9 is less than 12. I understand what you're thinking, but a greater negative is less. Think of it this way, right? If you have like a credit card, right? Who has less money? Somebody that owes $9 or somebody that owes $12? The person with the greater negative, the greater deficit, has less money. Further to the left means less than. Is negative 4 greater than or equal to negative 1? Well, I know it's not equal to, but what does greater than mean? Is it further to the right? Well, now we got 0, negative 1, 2, 3, negative 4. Is negative 4 greater than to the right of negative 1? See, if you can think of a number line, this utterly becomes nonsense. You can see that and go, that is false. A greater negative is not greater. It is actually less than a smaller negative. Is negative 6 less than or equal to 0? If you're not sure, here's 0. Where is negative 6? This says negative 6 is less than or equal to. That means negative 6 is to the left of 0. That is true. All right, where are we at? Absolute value. I'm going to go ahead and erase this. When we talk about absolute value, what a lot of people do is they'll give me kind of the book definition, and that doesn't make me sad. They go, well, an absolute value means that the number is always positive. I like to ask the question, why? Why is it always positive? And you're like, well, because I told my teacher that, and they gave me a gold star, and I felt good about myself, so I knew it was always positive, right? But that doesn't make it true. So why is absolute value always positive? Well, it has to do with what absolute value means. When we talk about absolute value is a number's, here's the key word. Some of you already know this. You're screaming at the screen. It is a number's distance from 0. Why did I underline the word distance? Why is that significant? Distance is always positive. If I drive my car to LA, and I drive, 150 miles, that is a positive distance. If I feel like a smartass and I throw my car in reverse and I drive 150 miles, It does not mean I went negative 150 miles. That's utter nonsense, right? Distance is always positive. If I sign up for a PE class, or if I'm involved in a sport and my coach says, hey, go run a mile, and I feel like a jerk, and so I'm mad at him, and I jog the whole thing backwards. You get to the end of that mile, and the coach looks at you and goes, that was a negative mile, now you owe me 2. It's utter nonsense, right? Distance is always positive. The person that's sitting in front of you is a distance from you. The person sitting behind you is a positive distance from you. Distance is always positive. So when I say what is the absolute value of negative 5, what I'm really saying is what number is 5 away from 0, right? How far is negative 5 from 0? If I go from 0 to negative 5, it has a distance of 5. Always positive. If I said what's the absolute value of 5, how far is 5 from 0? It is still 5 away. If I take the two numbers, 5 and negative 5, they are the same distance from 0. So both of their absolute values are positive 5. Now don't fall for it though, because you're like, oh sweet, so then the next one's going to be 5 and the next one is going to be 5. No. Look, you have to still do order of operations. The absolute value is kind of like a parentheses. So I'm doing this, I have to take care of this first. So what is the absolute value of 5? Out of here comes this positive 5, but this negative is waiting for it, right? And it gives me the opposite of. It gives me the opposite answer. So the absolute value of 5 is positive 5, but then I end up with a negative 5, or just negative 5. On this one, and he's like, oh, I know this. 2 negatives always become positive. No. I mean, most of the time, yeah. But what do I do first again, right? The absolute value, the grouping. What is the absolute value of negative 5? Out comes a positive 5. That negative is waiting on the outside that makes my answer a negative 5. So it's not that the answer is going to always be negative, but the result, whatever comes out of an absolute value, will always be positive. This next one is more like what you're going to see in the homework. If I have negative absolute value of 8 minus 5, once again, order of operations, starting on the inside, starting in the, not the parentheses, but they're like parentheses, the grouping. You do 8 minus 5 is, and then you bring the rest down. Absolute value, bring the negative. What's our answer? You're like, it's always positive. Be careful, right? What is the absolute value of 3? Out comes a positive 3, and so I end up with negative of 3 or negative 3. The only other term that they're going to use that you need to be comfortable with is going to be additive inverse. Additive inverse is another way of basically just saying the opposite. But what does it really mean? Additive inverse. What can I add to cancel? What can I add to 15 to cancel it out? Well, 15, if I had a opposite, negative 15, they would cancel each other out. What is the opposite of negative 9? A positive 9. If I had a negative 9 and a positive 9, they would cancel each other out. Additive inverse. But if they use that word, it just means opposite. I'm not as big on that. We're going to use it a little bit later, but I just didn't want you to freak out when you saw it in the homework.